Another way that we write roots in mathematics is by using a fractional exponent. And as you can see by the definition on the next page of the packet, it says that the nth root of a number a is always equal to a raised to the 1 over n power. So like in a few of the examples here, say for example I had the square root of a number m, that's always equal to m raised to the 1/2 power, or if you want to change it to a decimal, m to the 0.5 power. So basically, this is a way of saying, well, what does an exponent that's not a whole number mean? What does a fractional exponent mean? It translates to a particular root. And I actually talked about why this is the case back in I think it was chapter 4, when I was talking about exponents and those sorts of rules. But the gist of it is that, like, because say I was to look at a pattern such as 2 to the first and 2 square, or actually let's use 4. I think I used 4 in the previous video. Like if I was to look at what is, what does 4 to the first power mean? That just means, well, 1 times 4. And what does 4 squared mean? It means 1 times 4 times 4. And I believe I talked about why 4 to the 0th power must be 1, because in a chain of multiplication you can't start with 0, you must start with 1. That's the intercept for such a pattern. But if we think about, well, what's in between 1 and 0, what about 4 to the 1/2 power? Or what about 4 to the 3/2 power? It's coincidentally just equal to 2 in this case, but it's not equal to 4 multiplied by 1/2, though that does equal 2. It's like, well, what is a half factor of 4? And if we think about what the square root does, it's the inverse of 4 squared. 4 squared, it's kind of the opposite expression. 4 squared means I take a 4 and I have 2 of them. Well, taking half of an exponent means taking half of a factor, which is equivalent to the square root mathematically speaking. And that's exactly what this definition is saying. That if I'm trying to take a square root, it's equal to a half power in the exponent. Or say, I was trying to think about what is a 1/3 power, what is a 1/4 power. Each of those baseline fractions is equivalent to the associated nth root. So, another example will be, well, what's the 4th root of 16? It's equal to 16 to the 1/4 power, or 16 to the 0.25 power. So all of this plays into understanding, well, what does an exponent that is not whole really mean? And we could even confirm this with a calculator, because what we know is, well, the 4th root of 16, that's just 2. Because, let me go ahead and get that typed in. The 4th root of 16 is 2. Because 2 to the 4th makes 16, as is what the definition of an nth root does. But if we check out this kind of equivalency that is stated, 16 to the 1/4 power, a common error that I've seen students do here is basically just taking 16 and multiplying by 1/4. If you do 16 times 1/4, that is just 4. But remember, an exponent is never the same. You're never directly multiplying the two numbers, which is why, if you're trying to figure out what this means, it's helpful to think of it as an nth root. Because, of course, that by the equivalency should also be equal to 2. Or, if we were to type that in as a decimal, it's all the same. It's all an equivalent expression equal to the 4th root. So say, in these examples, I ask you, well, instead of evaluating, how would we rewrite these using a fractional exponent? And also another value of this is if we can change a root to an exponent, we can use the laws of exponents to actually simplify or solve particular expressions. But basically, if I was taking the square root of a number, like square root of 729, since that is an index of 2, that would mean that this is equivalent to a fraction of 1/2. So this would be equal to 729 to the 1/2. And that just means that, if you wanted to evaluate a root, you could do so by using an exponential fraction like that. You could use the exponent key and raise a number to a fraction, and that's identical to taking a root. And this is how I always take roots. I don't use the cube and nth root function, because to me it's just easier to just use a fraction to do it, because it's equivalent at the end of the day. And of course that's equal to 27, because 27 squared is 729, and taking a half power means taking half of the factor out of it, and since it is a perfect square, half of those factors would just be 27. Or say I wanted to do the cube root of 42, there is no easy since 42 is not a perfect cubed, it's not going to be a nice pretty answer. And of course we could always evaluate what that would be with the calculator, getting an irrational value. We could also do that just by taking 42 and raising it to the 1/3 power. So 1 is always in the numerator, and the denominator is always n. That's one of the ways you could remember. The index goes on the bottom. And so this, we could approximate this. But, the goal of this was not to actually get the answer, but to just rewrite it. And so, the next one would be 188 to the 1/4 power, and those would all be equivalent. Or if we wanted the 7th root of 2187, that would be 2187 to the 1/7 power, and so on. Also, you might notice that each one of these are called unit fractions, or fractions with 1 in the numerator. But what if we had, say, looking at a few of these other examples, what if we had a different fraction in our exponent that had a numerator that was not 1? How do we deal with it in that case? And basically that's how we expand our definition to, well, what happens if we had a to the m over n power, not just 1 over n, but further. And basically it's taking this key idea and translating it a little bit further. Because say, for example, we had a to the 3/2 power. Well, 3/2 is equal to 1/2 times 3 by basic rule of mathematics. And the exponent is just a normal number, so you can, change its form using basic fraction math if you want. And well, looking at it this way, well, a to the 1/2 power, as we, as I said above, is equal to the square root. So I could rewrite this as the square root of a cubed, because remember, when we have something multiplied in the exponent, that's equivalent to stacking it. And basically, this is the definition here is just communicating that idea which I'm expressing. But I could have also arranged it in a different order. I could have also arranged this as equal to a to the 3 times 1/2 power, which would be a way of saying, well, I have a cubed to the 1/2 power, which would be equal to the square root of a cubed, because again, a 1/2 power just means the square root. So essentially, if I have a fractional exponent, it's equivalent to a radical expression in two forms, which are always equal. And this is, what this generic definition is communicating. If I have a raised to a fraction, that's always equal to the nth root of a to the m power, or the nth root of a quantity to the m power. Either way, it could be arranged. By the law of exponents are equivalent. So looking at a few examples, say I wanted to figure out what is 8 raised to the 2/3 power. It can be helpful sometimes to change it to its radical form, and that way maybe it will help me figure it out a little bit better. So like in the case of, and another helpful thing to remember is the denominator is always the index. The one on top is always going to be, it's going to remain the power. So like here, well, the cube root of 8, that's just 2, because 2 cubed makes 8, and then there's still a square left over on the outside, and 2 squares, of course, 4. So what I get from this is that the 8 raised to the 2/3 power is equal to 4. And of course, you could do this with any calculator, and it will be able to figure that out for you as well. But the point of this is try to bring sense behind what's happening, because this would confuse a lot of people, because it's not a direct multiplication. If you're thinking about, well, 8, how do I multiply that into 2/3? That's not a whole number, but it's not multiplication. It's a matter of taking 1/3 of the factors, 2, and squaring it, 4. So it's a little bit strange. And say I had another example. You can take fractional exponents of negatives if the denominator is odd. And remember, if this were an even denominator, this would imply a square root. So working on a negative would not necessarily be good. But you could always check it out and type it in. But in this case, a -8 to the 4/3 power is 16. And I could always figure that out by thinking about, well, this is equal to the cube root of -8 to the 4th power. And the cube root of -8 is just -2. And -2 to the 4th would just be 16, because it is 4 times, so it always goes back to positive, and 4 2's make 16. So looking at a few other ones, let's try to do a couple of these without a calculator, but because anybody could just type this into a calculator and get the answer. But so in the first one, 9 raised to the 3/2 power, and so what I always suggest doing is first translating it to a root. So Since the denominator is 2, that means it's going to be a square root of 9. And then that whole thing will be cubed. So the number on top will always go on the outside or inside. You can put it either location depending on which you think is more useful. But in this case, I think, well, the square root of 9 is obviously 3. And 3 then cubed would be 27. And so I could, figure out what 9 to 3/2 power would be by using radical thinking. And doing another one, if I have 125 to the 2/3 power, I want to be careful because here now 3 is in the denominator, so 3 is my index on my root. And I'd want the cube root of 125, and that whole thing would be squared. And so this would be, the cube root of 125 is just 5. 5 squared would make 25. And sometimes, you can figure it out without too much of a headache. Whereas other times, it might, again, it could be irrational because if you're taking the square root of, say, 7, there's no easy number that will work. Now, another one I wanted to mention is, what if we had a negative? Because if I was taking the square root of a negative, that would be a problem. But remember that when an exponent is only applied to what it's directly next to, and if that negative is not in parentheses, what this means is, well, really this exponent's only applied to the 36 and not the negative. So this would be negative, and then it would be the square root of 36 cubed. Basically, that negative would not be a part of the input. And so the square root of 36 is just 6, so I'd have negative 6 cubed, and that would end up giving me negative 216. And so that would work all fine and well. But say looking at number 5, this one would be a problem because here the entire negative number is raised to that power. So this would mean it's the square root of negative 36 to the 7th power. And since the square root of a negative is not real, this sometimes you could get a not real solution from this. And again, we could always type it into a calculator and see what it says. And, we'll run into that same error. But if you type in like number 3, again, as you see it, the calculator should be able to interpret the order of operations correctly and be able to solve them. But it is a matter, you got to type it in right? And so that's, one of those things I wanted to mention. And last but not least, sometimes it's helpful to just practice rewriting them. And this would be a very common homework or test question. It's like, here's an algebraic expression, rewrite it using a fractional exponent. Like say, for example, I had the 4th root of x to the 5th power. Basically, I could always translate that directly back to an expression. Even if I don't know what the number is, I could just rewrite it as x raised to a fraction. And remember, it's always the power on top and the index on bottom. And so like in the next one, this would be y to the 7th, 7/3. And this one would be j to the 14/2. Because remember, when there is no number, it's not 1. It's always referent to a square root. So the invisible, when there is no number, just remember it's a denominator of 2. Because there is no such thing as a 1th root. And also, sometimes you can even use fractions to simplify. Because when you have a fraction, it's, sometimes that fraction will simplify. Like 14/2, that's just equal to 7. So oftentimes we could actually simplify an algebraic expression by lowering the terms of the expression. But actually, in this case, more correctly, it should be an absolute value because it's a square root. And as I was saying before, when you have a square root, it should only produce a positive answer. And j to the 7th wouldn't necessarily be positive. So there's certain little details that sometimes can get overlooked when you're trying to simplify a fraction of an exponent, which, if you kind of think about them, it will make, it can help. And so another one would say I would have u to the 14/7 power. 14/7 just makes 2, and this would be u squared. This one I would not need an absolute value because it's an odd powered index. And, well, technically the inside couldn't be negative because it was the 14th, and neither would u squared, but basically, you do need to pay attention to those cancellation rules. Occasionally it can cause hiccups, and often it might just be a missing absolute value.